Okay, so I'm going to go through questions from the practice exam because I'm fearing that you're not going to have, we're not going to have enough time to cover everything that needs to be covered during our tutoring sessions. So bear with me as I go through this. I'm going to do one recording for each question, and so that you can look at them individually as you need. All right, so question number one. Statistics students conducted an experiment to see if a student could determine the color of a gummy bear from its taste. Participants were blindfolded and then randomly assigned to chew either a green or a white gummy bear candy and guess the color. Of the 121 students who participated in the experiment, 97 correctly identified the color of the candy. If there is no relationship between the color and the gummy bear taste, we would expect the proportion of students who guessed to be 50%. Place an X next to the blank of the hypothesis that would be used to test if the proportion is higher than 50%. So on each of these problems, there's one correct answer. The correct answer is this one. But more than that, we should talk about why the other ones are incorrect. For example, this one makes a reference to a p-hat. And our null hypotheses are always references to population proportions, not to sample proportions, which makes that one wrong. It makes this one wrong. And it makes, well, the last one isn't wrong because of the p-hat. The last one is wrong because the H0 claim has an inequality, whereas the H0 claim always are equalities. Okay. Second question, which of the conditions must be met for the hypothesis test to be valid? Well, we want the p-hat value that we get from our sample. We want that p-hat value to be normally distributed, but there are some distractors here. For example, population proportions are never normally distributed. Proportions are not normally distributed. They are either yes or no, and there's no normal distribution. This is a distractor to remind you of a condition for a hypothesis test for means. This one is the correct answer, which we would define as the expected number of successes is greater than 10, and the expected number of failures is greater than 10. Now, this answer looks really similar to that, but it's talking about not the expected number, but rather the ones that we actually saw in the sample. This is a correct answer for a different question having to do with confidence intervals. So confidence intervals, we only look at the sample, but on a hypothesis test, we look at the expected numbers. Observations must be independent of each other. That is also an assumption that must be made. All right, so given our situation, calculate the test statistic and the p-value and show all your work. All right, well, the test statistic in here is a z-value. And by the way, we can see that they actually give us the calculation here, the formula for this. The z-value for proportions is p-hat minus p-naught all over the square root of p-naught, 1 minus p-naught over n. All right, so how does that play out here? Again, it is p-hat minus p-naught over square root p-naught, 1 minus p-naught all over n. Now, our p-hat is what we observed in our sample. We observed 97 out of 121, 97 divided by 121, which was about 8.01, let's call it 8.017, all right? 0.8017 minus our p-naught, which is the value from our H0 claim, 0.5, all divided by the square root of 0.5, 1 minus 0.5, all over our sample size of 121. Now I'm going to go alpha F1 to get a fraction, so it looks exactly like what I wrote. Oops, go back up there. Minus 0.5 all over the square root of, and I'm going to do another fraction, alpha f1, enter, of 0.5 times 1 minus 0.5, close that up, and then underneath our sample size. So we got a z value of 6.637. So our observed test statistic, 6.637. Now, how does that relate to the p-value? Well, we imagine a distribution centered at 0.5 with a standard deviation of whatever that is, okay? Oh, I'm sorry. No, not centering this at 0.5. This is a standard normal. This is a standardized example. So this is 1, 0, and 1, and we are way over here at 6. There's very little distribution out here at 6.6 and above. Now, how would we calculate that? Well, we're going to use the norm CDF functionality, which is under second distributions, normal CDF. Our lower bound is going to be this statistic. We're really trying to find the probability that Z is greater than 6.637, which means our lower bound is at 6.637. Our upper bound is the largest number that we can put into our calculator, or about that, 1.1 times e to 1 times 10 to the 99th, e to the 0 and the 1 same, and we get 1.609 times 10 to the negative 11th. For a little perspective, that's 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 10 zeros, followed by a 1.609. But I think we can just write that down as 1.609 times 10 to the negative 11th. All right, amazingly low test statistic, or sorry, p-value. Write a statement evaluating the null model based on your p-value. Well, because the p-value of 1.609 times 10 to the negative 11th is less than. Now, in this case, we look back at our formula sheet, and the instructor has said any p-value less than 1/1000th is extremely strong evidence. Well, that's what we have then. We have it's being less than 1/1000th. And because of that, we would reject the H0 claim and state there is extremely strong evidence. And then what do we think we proved? That people can determine color of gummy bears by taste. All right, now this next part, let's find the 95% confidence interval. Again, your instructor has given you the formula for the 95% confidence for the confidence interval. It's right here. P hat plus or minus Z star square root P hat 1 minus P hat over N. So let's go ahead and say that means we need There we go. And our p-hat value again was 0.08017. Our z-star value for a 95% confidence interval is given right here, is the infamous 1.96 times 0.081017 times 1 minus 0.0817, all over our sample size of 121. So let's go ahead and calculate that. 0.8017 minus 1.96 times square root of, and again, I'll make a fraction, 0.8017 times 1 minus 0.8017, close that off, sample size of 121. Enter. So our lower bound for our confidence interval, 0.73 plus 7. Let's go up here twice. And we go alpha left arrow. Oops, sorry. The second left arrow. Get over to the far left-hand side. Change that to a plus sign. And we get 0.8727. And that's our confidence interval. And what do we mean by that? Well, we think that the plausible values for the true proportion of people who can determine the color based on the taste is somewhere between 73% and 87%. All right. Now, little side note here, both of the calculations here and here can be found directly on the calculator, but they don't show the calculations being done. I show this not so that you can do this in lieu of it, but rather because it's a way of checking your answer. If I go stat, tests, and what we first did was a 1 prop z test, 1 for one sample, prop for proportion, z because z was our test statistic. If we set our p-naught was 0.5, that 97 out of 121, we had 97 successes out of 121 trials, that our h-naught claim is that p is greater than 0.5. And we say calculate. We can see those numbers popping up. There's a little bit of rounding, but I wouldn't worry too much about that. For the second number, stats, tests, and this is a 1 prop z interval. Again, 97 successes out of 121 trials, and we wanted 95% confidence. And you can see that those numbers, again, close because there's just a little bit of rounding. And that's question number 1.